This is the third installment of Lecture 2, so Lecture 2.3. We're going to be going over math functions and methods in Java. One of the convenient things about the Java language is that it comes with several predefined classes, so libraries, built into Java natively. Some of those that you have been exposed to so far, scanner and printline, would be methods that are components of classes which are built-in standard to Java. Another one of these classes that is natively built into Java is the math class. The math class provides several standard mathematical methods. And one of the nice things about this is that you don't have to import the math class to be able to make use of these methods. Each one of these methods is going to return a value. So this idea of returning a value is something that we're going to talk more about in detail coming up. The general syntax for making use of these natively available math methods from the math class is as follows. You have some variable that you wish to assign a value that is going to result from one of these math methods. So the variable here is named return value, and you have an assignment operator, and the value which is going to be assigned to the variable return value is going to be given by math.methodName with the parameters or arguments being given to the method in parentheses. So what is happening here is we have an object referred to as math, and we're accessing the methods which are a part of this object through the dot operator. So math dot, and then whichever method you would like to use, and then in parentheses the arguments to that method. And this is going to, as I said, return values, one or more values, which we are going to capture into this variable here, which we have named return value. So when we return these values are not inherently printed to the console. Each method is called by its name and is passed any necessary arguments, and each method produces and returns a numeric result. Now that result, as we said, is not necessarily printed to the console unless you issue a printline command to print it to the console. The result of the mathematical operation is returned, then can be used as part of a greater expression, so such as assignment or printed or any other expression. So here are examples of what we're saying. So let's first of all define a variable called square root. We'll declare it as a double type, and we'll assign it the value which results from math.square root of 121, and we terminate the statement with a semicolon. So the right-hand side expression is going to evaluate first in any assignment situation, and the right-hand side expression here is the math operation square root. So we are accessing the square root method, which is a part of the math class, and in this case, it's this class is instantiated, so therefore it's the math object, and we're accessing the square root method of the math object, and we are passing that method the argument 121.0. Now, this 121.0 is a double literal. The square root of 121 is going to be 11, and it's going to return it as a double. So therefore, square root then will be assigned the value 11.0. So then, if we wish to display that to the console, we would have to issue a printline statement and pass to the printline statement the argument square root here being the variable name. So square root is the variable we declared, and we're passing that variable to the printline statement, and the value which is stored in square root is printed to the console, 11.0. So similarly, we have down here using the absolute value method, which is part of the math object, the math class. So we take the absolute value of negative 50. That returns the value 50, and it's an integer return. And this value 50 is assigned to the integer value absolute value. So, sorry, I said integer value. I mean to say integer variable. So we have an integer variable called absolute value, and we assign it the value which results from the absolute value operation of negative 50. So absolute value now has a value of 50. When we print that to the console, 50 prints out. And then in the final example, we have a variable x of type integer, which has been initialized to the value 3. And then we're going to have a print line statement, and we are going to pass as argument to the print line statement an expression. More accurately, we're going to pass the result of this expression to the print line statement. So the the math.min method is going to find the minimum value between the variable x and 7. The variable x contains the value 3, so 3 and 7. 3 is lower than 7, therefore math.min will return 3. Then the next operator in precedence would be the plus, so we would do 3 plus 2, which results in 5. 5 is the result of this overall expression. 5 is then passed to the print line statement, which is shown on the console. So hopefully this makes sense. The math method itself does not print anything to the console. The math method returns a value. So the math class contains methods which are helpful. So square root, absolute value, min, max. These are all methods which are part of the math class. Along with the methods which are contained in the math class, there are also two constants which are defined in the math class. Those are e and pi. E being Euler's number and pi being 3.14159 and so forth. To make use of these values which are part of the math class, we access the math object and then use the period operator to access the value pi, which is part of the math class. So math.pi will evaluate to the value 3.14159, so forth. So math.pi times radius would give you this area of a circle with radius equal to the value stored in the variable radius. We've mentioned several times that doing integer division or typecasting a double to an integer truncates. It does not round. If you wish to round a number in Java, the math class has a method which may be used for rounding. So if the argument is of type double, it returns a whole number of type long. Long because a double precision floating point number may be too large to represent an integer. So if you pass a double to the round method, it will produce an output which is the rounded version of that double as a type long. Other operations that are similar to round but different, floor and ceiling. So the floor function, it would take, say, the value 3.2. Floor is going to truncate and take that down to 3, while ceiling is going to always take it to the next value up. So anything greater than 3 is going to evaluate to 4, while anything less than 4 in the case of the floor function would evaluate to 3. So it returns the largest or the smallest whole number that is less than or equal to its argument in the case of floor. In the case of ceil, it returns the largest whole number that is greater than or equal to its argument. So floor always rounds down, ceil always rounds up. Something to know, if you provide an input of type double, then the output, which is returned, will also be of type double, but it will be a whole number. So rather than returning an integer or a long, it will return a double, which has a decimal component equal to 0. So past 3.2 to floor, it will return 3.0, which is different from round, right? Because round is going to return a type long if it is given a type double. In all the discussed methods, round, floor, and ceil, none of them return integers in the case where a double is provided. So ceil and floor both produce double output, and round produces a long output when given a double. So if you were to need to store the result of any of these methods in an integer, you would need to use a typecast operation. So here's an example. If we declare a variable of type double and name it start, and we initialize it to the value 3.56, then we declare an integer variable called nearest, and we assign it the value which is produced by the expression, typecast to integer, whatever the result is from a rounding operation applied to the value start. Okay, so math.round, when we pass it the double 3.56, round is going to produce a long. It will produce a long with the value 4 because 3.56 rounds up to 4. Then we will typecast that long value 4 into an integer value 4. And that integer value 4 will be stored in the variable nearest. Then we will create a variable called lower bound, which is also of type integer. We will apply the floor function, and we will typecast it to an integer as well. Remember, the floor function is going to round down always, no matter what the decimal component is. So passing the double 3.56 to the floor method, it will return the double 3.0. The double 3.0 is then typecast to an integer, which truncates the decimal, so the integer 3 is stored in lower bound. Similarly, we will declare a variable called upper bound of type integer, and we will assign it the value which is returned by ceil, and we will typecast it as an integer. So ceil is going to always round up, and we are giving it a double value as an argument, so it rounds it up to 4. Then we are typecasting the resulting double value into an integer, which truncates all of the decimal, which results in the integer value 4, which is stored in upper bound. So then the nearest integer to 3.56 is 4, the lower bound is 3, and the upper bound is 4. Sometimes when you're dealing with floating point numbers, you'll notice that the result from doing various operations to floating point numbers is not precisely correct. A good example of this would be in the situation where you divide 1.0, which is a double, by the double 3.0. In reality, this value is 0.3333, so forth, 3 repeating. So this sort of repeating decimal point goes on for infinity. Well, that's not really possible to represent in a finite memory space. So therefore, the way that this is stored in the floating point number is just a long list of 0.3s. So actually, if we do not allow the 3 to repeat infinitely, and we just stop it at, say, 6 repetitions, 0.33333 is less than 1/3. So for this reason, if we sum 1 divided by 3 plus 1 divided by 3 plus 1 divided by 3, where each of these are doubles, then the result is actually going to be slightly less than 1, for the very reason that each of the values which was returned from dividing 1 by 3 is going to be a truncated representation of 1 divided by 3, which is actually slightly less than 1/3. So when you add them together, you get something that is slightly less than 1. Another example that you can test out is if you were to issue a print line statement in which you pass as argument the expression 0.1 plus 0.2, the correct result is obviously a precise 0.3 mathematically. However, the output which is displayed to the screen is most likely going to be something like 0.3 followed by many zeros and a 4. This is because floating point numbers are a near approximation of the real number. However, this approximation is not perfect and occupies a finite amount of memory, and therefore the numbers may be somewhat imprecise. A common requirement is to round to a certain number of decimal places. So perhaps the requirement is to round to the nearest penny amount, right? So this would be to round to the nearest hundredth place. So if that requirement is made, there's a simple algorithm to accomplish this. You multiply by 10 to the n, with n being the number of decimal places to which you would like to round, apply the round, and then the rounding function, and then divide by 10, again raised to the number of places to which you intended to round. So as an example, to see this, let's say we wanted to round the number 0.3333 and so forth to the nearest hundreds place. So then we would multiply the result, result being 1 divided by 3, by 100 to move the decimal place 2 places to the right, resulting in the value 33.33 and so forth. So now result contains the value 33.33 and so on. At this point, we can apply the rounding function, which will produce a double that has a fractional portion which is equal to 0. So the result of applying round to 33.33 and so forth is 33.0. Now we can divide the result by 100 and store this back into the result. The overall effect was that we rounded it to the hundredths place. If this doesn't make sense, take a few moments to look at it and process it and think about why this works and what we were trying to do. We were trying to round this original number to the hundredths place. So the rounding function that we have will always produce a decimal that is 0. So if we were to have applied the rounding function directly to 0.33 so forth, then we would have just wound up with 0.0. So we multiply by 100 to move the decimal over 2 places, apply the rounding function, and then divide by 100 to move the decimal place back to its original location, and then print the result. Here's a list of useful methods which are included in this math class, and for an exhaustive list, refer to this link, which is the Java docs. So part of learning to be a programmer, in general and in practice, is to get used to reading the documentation for the language. Documentation for programming languages, you'd be surprised at how dry it is. It's not very entertaining reading, but it has all the answers to the various questions you may have about proper ways to do things in a given language and different methods which are built into the environment. So referring to the docs to get an exhaustive list is a great way to get more familiar with reading programming language documentation, specifically Java documentation. But here's a short list of ones that you may find useful. Absolute value, round, ceil, floor, we've talked about those. Log base 10, max min, power. So if you wanted to raise a base to a specific exponent, it'd be useful: square root, sine, cosine, tangent. So notice the number of arguments each of these take. So power requires both the base and the exponent. Max and min requires two values to be able to decide which of these is either the max or the min, which is the larger and which is the lower. But several of these also take only a single value. Then also notice as a last note, math.random. Math.random does not take any arguments, but rather it produces a double which is between 0 and 1 with uniform distribution. As a case study, we're going to go through the development of a program that will print this system of characters onto the screen. So we have an octagon followed by what we're going to call a teacup, then a stop sign, and finally a hat. So let's just take a first crack at this, a very unstructured approach. We'll create an empty program with a main method, and we will just highlight all these lines shown here and just copy and paste it into the main and surround each with double quotes and the print line statement and run to see what the output gives. So more or less, we have done exactly what we said. We created our class. So every program requires a class if it's going to be executable in Java. And we called it figures1. And remember, your class name must be the same as your file name. So the file name would have to be figures1 as well. Figures1.java. And then our main method now contains the exact output we wanted, just surrounded by double quotes, and each line is the argument to a print line statement. With a few caveats here. Notice that anywhere we wanted a backslash, we had to put a double backslash because we had to use the escape sequence to achieve a backslash character in a string. So we had to modify that. Other than realizing we would need the escape sequence, we were able to just copy and paste the desired output into this program. This first approach to the program is ugly and unreadable. Let's go through specifically what's wrong with it. First of all, the style was very poor. We had no comments explaining what we were trying to achieve and what each of the code segments achieved. The only comment we had was it was written by someone who was not a scholar. There were no blank lines in the code to help show segmentation and give it structure. It was completely unstructured in that we had many small steps with no intentional grouping, so that it was completely, it was not very easy to follow and make sense of. And finally, it was very redundant. There are many places that we were drawing the same shape over and over, and we were completely reduplicating the work necessary that we had already done to draw those shapes on the screen. Making the program better then, happily, is just a matter of addressing each of those concerns. So improving the style, providing structure, and then removing the redundancy. So stylistically, we're going to add comments and blank lines to give appropriate separation to the code, and this separation will allow us to group tasks together that make sense. Redundancy. The redundancy is going to be a little bit harder to fix, significantly harder to fix than it was in the receipt program, but we will fix the redundancy, but we're going to address the other issues first, and then the redundancy we'll fix last. So here is our improved first approach. We have included some comments, and we have added some spacing to show the groupings that we have in place. So we're printing the egg, then we're printing the teacup, and then below that we would put the code to print the stop sign and the rest of the figures. But it's still not very good. What if we needed to print 2 eggs or 2 teacups? We would not really have a means to do that other than just having to select and copy and paste this block of code again in the location in which we wanted to print another egg, or do the same thing with the teacup. That's that is not a good programming method. One of the tenets of good programming is the acronym DRY. So in general, a good programmer should attempt to write dry code, and dry code stands for code that does not repeat yourself. So if you find that you're coding, if you find that you're coding the same set of statements necessary to print an egg over and over in order to print multiple eggs, you're repeating yourself, and that's bad coding. So this is still not a very good approach to solving this problem, even though we have added comments and separation. So here it is written out explicitly. If we needed to have 2 eggs or 2 teacups, we wouldn't have any other choice than to duplicate the code, in which case we're repeating ourselves. That would create redundancy. It's not dry, we are repeating ourselves. So we need to address this. As well as addressing that issue, we still have yet to address the larger redundancy issue, which is we're drawing the similar shapes in multiple places in the program over and over again. So we can solve both of these issues utilizing methods. Notice the structure on the right. Inside a Java program, you have a class, and then inside of this class, you have methods. So we have so far made use of the main method, but we can also introduce other methods. So in general, a method is a named group of statements which accomplishes a specific task. So a structured approach to decomposing a problem into individual pieces that you can code into methods is called procedural decomposition. You divide the problem into tasks and denote the structure of the program based off the tasks that need to be completed. This will eliminate redundancy by allowing code pieces to be reused in multiple situations. Now, it's important to understand that for any given task, there are multiple possible decompositions. Some are better than others, but there are situations in which multiple decompositions are equally valid. It's almost like adding, when you make a method, it's almost like adding a new command to the Java language for you to make use of. So just as there are methods built into the math class that give the square root of a number as output, we could write our own method to provide the square root as output. So in this situation, we're going to write methods which accomplish pieces of the overall task in such a way that we do not have to repeat ourselves unnecessarily. Before we can make use of methods, we need to discuss the syntax necessary to declare a method. So we have to declare variables before they're able to be used for storage, and similarly we have to declare a method before we're able to make use of it as well. So the general structure for declaring a method would be public static void, and then name, and then each of the statements involved. Now, public static is part of the incantation, you might say, to making to declaring a method. The word void here means that nothing will be returned. So when we were dealing with methods in the math class, they returned values. This method that we're going to be declaring is going to print something to the screen, but it's not going to return any values. So a method that which does not return a value is void. Then we have to give our method a name. As with any identifier, we need to have names which are informative and contribute to the overall readability of the program. So an example of a method would be public static, and it's void because it doesn't return anything. And then the name is going to be camel case, print warning. So I know what it's going to do. It's going to print a warning. This is helpful. It's informative. And then the statements, which are housed in the method, are a print line statement with the string "this medication causes drowsiness," and a following print line statement which says "be careful operating machinery." Once a method has been declared and the statements coded, you can put it to work by calling it. That's the terminology we use when we make use of a method. We would say we call the method. So think of the method as an employee and the main as the manager. So the main will call various methods and make use of them to accomplish the overall task of the program. So the employee doesn't start working until the manager tells him or her to. That's important to understand. The methods which you house in a class are not executed unless they are called by the main method. The syntax for calling a method would simply be the name which was given, followed by open parentheses, close parentheses. Now the reason that there are no arguments to pass the method is because we did not declare the method to have any arguments. So an example from the previous slide, we created the method print warning. So in order to call the method print warning, we would simply type the name print warning followed by open and close parentheses and a semicolon. So here's an example of a class which contains two methods. It contains a main method and then it contains a print warning method. Notice here that the print warning method has a method description so that we know what it is intended to accomplish, and that it is named appropriately, as we discussed before. Print warning tells us it's informative that it will print a warning. So when this Java file is executed, the main method is where execution begins. So there's nothing on this line. We have a comment. It says print the warning by calling our handy method. So this is good. We have a comment that tells programmers what this is intended to do, but the compiler is going to ignore this, and at runtime this will be ignored. We are going to encounter this call to the print warning method. So at this point of execution, the program will jump down to the first line of the print warning method. And the first line is a print line statement. It will print "this medication causes drowsiness." And it will continue to the next statement, which is a print line statement, and it will print to the console "be careful operating machinery." There are no statements left in the method, so at this point the program will return to the line from which it entered the call and continue to the next statement. So then it would print "we are not kidding." To design an algorithm and decompose it into methods, begin by figuring out how to solve the overall task, how to complete the overall task. This is subjective. There may be multiple ways to accomplish an overall task. But once you've decided on your method your algorithm to accomplish the overall task, notice the structure and observe where you are being redundant. Observe where you are repeating the same operations. At this point, define methods that will accomplish these repetitive tasks, and give the group of statements which accomplish that task a name, and this will become the name of the method. Then the main method will use the other available methods along with any statements which are coded directly into the main method to accomplish the overall task, thereby eliminating repetition. Imagine that we were attempting to write a program which would print the lyrics to a children's song to the console. This particular song is very repetitive and only repeats 2 lines of lyrics over and over again. So writing the entire song with each line of the song in a dedicated print line statement would be extremely repetitive and would be highly redundant. A better way to go about this would be to recognize that the overall task is to print the lyrics to the children's song to the console, and then notice that in doing so, you're repeating the same lines of the song many, many times. So then, these lines, this group of lines which are repeated and printed to the console multiple times, could be housed in a method. So we'll create a method called sing and annoy, because that's what it does, which will print to the console the words baby shark, followed by carriage return, followed by this line. And it prints some lyrics from an overplayed hit song from a children's YouTube channel. Then in our main method, we will make use of this sing and annoy method. So when we run this Java program, remember the program must be named repeatit because the class name is repeatit. So this is repeatit.java. When this program runs, the program will begin to execute at the first line of the main method. So the first thing that we encounter is a call to the sing and annoy method. The sing and annoy method starts to execute at the first line of the sing and annoy method, which will print baby shark. Then we'll move to the next line, the next statement, which will print do 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 do. Once there are no more statements to execute in the sing and annoy method, the program will return and move to the next statement after the call. At this point, it encounters a print line statement with no arguments, which has the effect of causing a carriage return, at which point we again call the sing and annoy method. So it will again print out baby shark, do-do-do-do-do-do. And then we'll encounter the end of file once it returns to the main method and the program has completed running. We have discussed situations in which we call a method from the main method. But you can also call a method from any other method as well. You can even have a method call itself. We'll talk about recursion later, but that when a method calls itself, that would be referred to as recursively calling. So we have a class here called methods example, and our main contains a call to message1, which is a method, and a call to message2, followed by the printline statement done with main. Message 1 contains a printline statement which prints out this is message 1. And message 2 contains a printline statement which prints out this is message 2, followed by a call to message 1, which will print out this is message 1, then return back into message 2 and print out done with message 2. So let's trace through this execution. When this Java program called methodsexample.java is run, message 1 is the first line in the main method, so this is the first thing that will be executed. It will execute the call to message 1. Message 1 will print out this is message 1. That's what we see as the output in the very first thing. The program pointer will then return to the call and move to the next statement. It will call message 2, so the program pointer will jump into message 2 and will execute the first statement, which prints this is message 2. Then the program pointer will move to the next statement, which is a call to message 1. At this point, the program pointer will jump into message 1 and execute the statements in message 1. The only statement there is a printline statement, which will print to the console, this is message 1. And that is indeed what we see on the output. At this point, the program pointer will return to where it entered from. So we got into message 1 this time via message 2. So our program pointer is going to return to where we called message 1 from and move to the next statement. At this point, it will print done with message 2. That's what we see on the output. At this point, we have reached the end of message 2, so the program pointer will return to the call which was placed to message 2 from the main, and will then continue to the next statement in the main. At this point, it's a print line statement which will print done with main to the console, and that's what we see in the output. The program pointer then moves past this statement and encounters the end of file, and it has finished executing. So it's important that you're able to step through and understand why this output occurs given this class and main method. Make sure that you understand and can trace through that yourself. In the previous example, we saw how the program pointer would enter into the various methods when they were called and then return to where they were called from and move to the next statement. This is referred to as jumping into and back from a method. So we would refer to this first call to message 1. When it is called, we would say the program pointer jumps into message 1, executes the statements which are enclosed in the method message 1, and then jumps back to the original location. Then it indexes to the next statement. At this point, it encounters a call to message 2. It jumps into message 2. Inside message 2, it encounters a call to message 1, which causes it to jump into message 1. And then it will execute the statements in message 1. Then it will jump back into message 2, finish executing the statements in message 2, and then jump back to the original location in main. And then it will index to the following statement. Hopefully, this is beginning to make sense and you're understanding how programs flow and how calls to methods affect the execution of a program. Now that we've discussed methods, their syntax, and how they affect program flow, let's take another crack at this shape drawing program and make use of these methods to reduce redundancy. So in this approach, we are going to identify the structure of the output that we wish to have. And based on this structure, we should be able to identify methods which we can use to prevent ourselves from having to repeat the same code in the program. And then we code these methods. So the structure of the output, shown here in yellow, we are going to draw an egg, followed by a teacup, followed by a stop sign, followed by a hat. So then this naturally separates itself into 4 methods: draw egg, draw teacup, draw stop sign, and draw hat. And this is nice because by coding each of these methods, if we wanted to draw 2 eggs, we could simply call draw egg twice, and we would effectively draw 2 eggs. So this prevents us from having to copy and paste code to achieve the same functionality in multiple locations. So here is the result from this decomposition and coding of the various methods involved in drawing this output. Now, we have the draw egg method, draw teacup, draw stop sign, and draw hat. Notice in our main, we are calling draw egg first. So our program pointer will jump into draw egg, execute all the statements, which will draw the egg on the screen. And then when it hits the end of the method, it will jump back to its previous location and go to the next statement. Then we'll jump into draw teacup, execute the statements, jump back. Then I'll move to draw stop sign, jump into draw stop sign, execute all the statements, jump back. Then it will execute the call to draw hat. It will jump into draw hat, execute all the statements, and jump back. Now this program is good However, we don't have much in the way of comments, and we are still repeating similar drawings in multiple locations. So for instance, the top of this egg is precisely the same as the top of the stop sign, which is also precisely the same as the top of the hat. So even though we are now able to draw multiple eggs without having to copy and paste, so major improvement, we are still repeating ourselves unnecessarily. To be able to solve this issue of remaining redundancy, where we're drawing the same pieces of figures in multiple locations, we may need to revisit our decomposition because, as we said, decomposition is a bit subjective, so maybe there was something we missed. So this time, our third approach to decomposing this problem, when we identify structure in the output, we're specifically going to be looking for redundancy. We want to eliminate any redundancy in the output. So we're going to prefer to create methods that eliminate repeating ourselves. And we're going to make sure this time we add comments so that we have good style in our program. So now we have finally identified all the pieces which could be drawn similarly. So notice in red we have the top arc, or the egg top we're calling it. In blue we have the egg bottom, and then in yellow we have the divider lines. So if we can write methods to perform each of these three tasks, egg top, egg bottom, and divider line, we will be able to remove the redundancy from the program. The resulting program then has 7 methods. So we have draw egg top, draw egg bottom, and draw egg, draw teacup, draw stop sign, draw hat, and draw line. So draw egg top, draw egg bottom, and draw line are sort of the smallest building blocks we'll use, and then we will use draw egg, teacup, stop sign, and hat to accomplish the overall functionality of each of the shapes. So we could almost think of the methods here which have green lines by them as being almost the shape primitives, and the blue lines are the methods which generate the shapes from the shape primitives, and then our main is going to actually cause the order of the shapes. So let's look at each of the blue methods. In draw egg, we are going to draw an egg top, then draw an egg bottom, and then we are going to do a print line statement which will cause a carriage return, so it'll leave a blank line after the egg. And draw egg top and draw egg bottom do exactly what they say. Draw egg top will draw the top of the egg, draw egg bottom will draw the bottom of the egg. So now we have drawn an egg without having to repeat ourselves and redraw the same shape. Draw teacup is going to make use of the draw egg bottom as well. Then it's going to draw a line, and it's going to again use a print line statement with no arguments to create a new line. Draw stop sign is going to draw an egg top. Then it's going to print the word stop and 2 bars in the middle of the egg, and it's going to draw an egg bottom and issue a new line. And similarly for draw hat, we're going to use draw egg top followed by draw line. So we have these shape methods which are making use of sort of the shape primitive methods to effectively draw these shapes. Then in our main, we are using our main almost as a high-level traffic directing method. So it makes high-level requests: draw egg, draw teacup, draw stop sign, draw hat. Notice how readable this is. So if you were to look at this program and you know that whenever a Java program begins to execute, it executes first in the main. So you look at the main and you see draw egg, draw teacup, draw stop sign, draw hat. This is immediately readable and you intuitively understand what this program is doing. Then to understand how it accomplishes that, you can simply look at the draw egg method. Okay, draw egg. Okay, this is readable as well. And we have documentation that tells us it draws a complete egg figure. Now, above the draw egg method, we have documentation. Also above the class, we have documentation that tells what the class does and who wrote it. Back to the draw egg method, though, we have the documentation, and then if for talking about readability, draw egg top, draw egg bottom, followed by a print line statement, that's extremely readable. I immediately understand, okay, drawing the top of the egg, drawing the bottom of the egg, and I understand from my knowledge of Java that print lines, an empty print line statement is going to cause a carriage return, so we're leaving a blank line. The structure of the solution, the structure of the program, makes the program easy to read. This is a better and appropriate decomposition to solve this problem with sort of maximum readability and minimum redundancy. So initially we had a very unstructured and very redundant solution with no documentation. By introducing methods and decomposing the problem into pieces, we were able to recognize that we would like to draw each of the shapes using a dedicated method. That way, if we wanted to draw more of the shapes, it would not require copy and pasting code, but simply an additional call to the method which draws it. So if we were to wish to draw an extra hat, we could simply call draw hat again in the next line. So this was a better approach, eliminated some redundancy, and made the code significantly more readable. But we still were left with this redundant drawing of similar shapes, such as the egg top, the egg bottom, and the divider line. So in our final decomposition, which is the most appropriate, we eliminated all redundancy and have methods to draw these so-called shape primitives, methods to draw the shapes based on the shape primitives, and then we have our main, which simply sits at the top of the call pyramid, so to speak, and issues high-level commands: draw egg, draw teacup, draw stop sign, draw hat. And the main doesn't have to get bogged down with and become unreadable due to excessive print line statements and redundant code. So how should you go about recognizing when and how to use methods? So in general, you should place statements into a static method when the statements are related structurally and or the statements are repeated. So in the previous example, we had the egg top that was repeated in multiple locations, so that made it a good candidate for being used in a static method, since we could make use of that egg top over and over again to eliminate redundancy and repetition. And the statements which we were putting into the static method were related because they should always occur in that specific order to draw that specific shape. You should typically not create static methods for instance a individual print line statement. So it would not make sense to define a method for a single line bit of code, such as print line statement, because it's already a single statement. Making a static method for this bit of code is not going to save any space or significantly contribute to readability. Also, you should not create a static method for unrelated or weakly related statements. So what this means is, let's say you had 30 lines of Java code. The blue represent the first 30 lines, and the green represent the next, or the first 15 lines, and the green represent the second 15 lines. you may think, okay, well, it is required that we use methods in this program, so I'll just encapsulate the first 15 in method 1, also a very bad naming system for a method, and the green into method 2. This is not appropriate. Just because this does effectively create 2 methods does not mean that these statements, which are housed in these methods, have any structural relationship, and in no way does this eliminate repetition and redundancy. So this is an inappropriate use of methods, which actually makes the code less readable. So the order of methods in a class does not matter, interestingly, to Java in terms of how they are listed. So in the previous example, for the shape drawing class, it did not matter where in the class the methods occurred. The main will always be ran first, regardless of where in the list of methods it occurs. So it's typical for either the main to occur first and all other methods to be grouped based on some reasoning after that, or for all of the other methods to occur first with the main occurring last. Either is acceptable. It's most typical for main to occur first with all other additional methods occurring afterwards. But just don't make it random and senseless. Be intentional about your ordering and grouping of methods and consistent about your ordering and grouping of methods.